All right, good afternoon, everyone. My name is Yibao. I'm going to talk about something related to sensors and health monitoring. Our last two speakers just talked a lot about some very interesting and informative topics about structural behaviors. But in reality, for example, after earthquake, it may not be safe for human beings to enter the building and do some condition assessments and judge whether the condition is still good enough or is still safe for people to live. So we developed sensor technologies to do this in a more efficient and safe way. So today I'm going to talk a little bit about AI technologies for sensor technologies. Okay, so a very brief introduction about my lab. I'm from Stevens, and our campus is at the waterfront of Hudson River. So if you happen to visit this area, feel free to let me know. I would like to give you a tour. And our lab is a structures lab. I'm a structural engineer, but our research mainly focuses on sensors and the robots. So first, I want to acknowledge my group, my students. I have graduated 6 PhD students. Currently, I have 9, and another 2 will join us very soon. And we also collaborate very closely with another colleague, Professor Wina Meng's group. She's a material expert. So I will talk a little bit about our collaborative research on materials. So today I will briefly talk about our research in 3 areas: sensors, materials, and structures, and a little bit information about their interconnections. So for materials work, I will mainly focus on concrete materials and particularly how we can use AI technologies to discover new materials efficiently. So for sensors work, this is the main topic for this presentation. We have worked on different types of sensors inspired by human beings. Like we use fiber optic sensors to mimic touch, and computer vision, like we use drones with cameras to see structural conditions. And we also have wireless sensors based on electromagnetic waves and sound waves for non-destructive evaluation. So this is the outline of this presentation. I will first talk about fiber optic sensors and their applications in normal condition, normal temperature, high temperature like fire, and some other sensing applications. Then I will briefly talk about our research on materials and structures. So first, the sensors. This is inspired by human body. We have sensory nerves over the body to collect information, and the collected information like force and temperature, this information will be delivered to central nervous system, and our brain will process the information and then will provide some commands to our organs or muscles to execute the decisions. In this way, we can control the human body for protection. And inspired by this concept, we developed fiber optic sensors, and particularly distributed fiber optic sensors. Fiber optic sensors are made using optical fiber, which is very thin, like fishing wire, but there are different methods for packaging the sensors. So the sensor is based on waveguide within the optical fiber based on total internal reflection. So when you use high purity fiber, we can achieve very long distance measurements. And here are some main advantages of this type of sensor. It's immune to EMI and is small, it's lightweight, and has stable measurement. There are 3 main types of fiber optic sensors, including grating sensors, interferometer sensors, and distributed sensors. The first 2 types of sensors, grating sensors and the interferometer sensors, are also known as point sensors because each single sensor can only provide information at a local spot. But distributed sensor provide a continuous measurement. The measurement distance, just 1 cable provide over 100 kilometer, actually more than 100 miles of measurements, and we can achieve very fine spatial resolution. In my lab, we have been using sensors with a spatial resolution of 1 millimeter. That means we have continuous sensors along the cable. It's like a combination of tens or thousands of sensors together. And this type of sensor can be used to directly measure temperature or strain change. Here I didn't have the animation, but this shows the briefly shows the mechanisms. So we input the light signal into the optical fiber, and when the light signal propagates along the sensor, it will generate some local acoustic signals. And there will be interaction between the light wave and the acoustic waves, or photon or phonon interactions will generate some scattering signals. And we utilize different types of scatterings. Like here, it shows technology based on Brillouin scattering. Brillouin scattering is a sort of nonlinear scattering phenomena. So the frequency shift is associated with strain and temperature, so that we can use the sensor to measure strain or temperatures. So I will talk about our basic understandings of the sensors and some representative collaboration, the applications. So first, we want to clarify that when we have a packaged sensor, this sensor will not provide the accurate measurement directly, because there's a layer of coating. This coating will have shear deformation, so the strain sensed by the optical fiber is different from the host matrix because of this shear effect. So we have to determine their relationship. But fortunately, we were able to do the mechanical analysis and develop this governing equation. Then by solving this governing equation, we can determine their relations. So this is very simple if you have a point sensor, because the sensor length is very short. You can consider the strain field as a uniform strain field. And there will be a development length, which is probably very familiar for our structural engineers, because this is general phenomenon for reinforced concrete or pre-stressed concrete. But in reality, the sensor is very long, so you always have nonlinear or non-uniform strain fields. So our contribution is that we solved this gravity equation in arbitrary field conditions without using AI. But recently, we use AI to solve this in a better, more efficient way. So we solved the sensor problem in continuous strain field conditions. But in applications, we often have to deal with discontinuous, like cracks. If the strain field is not continuous, then when the sensor passes through the crack, well, originally I thought the fiber will be ruptured, and then we will not have the signal anymore. But we did the experiment, and we found that actually the sensor didn't fail, because there's a protection layer, the coating. So because of the coating, the abrupt strain change will be averaged over a longer distance. So we were able to detect the cracks as shown as peaks. Each peak corresponds to a crack. And if you look at this plot, the horizontal line is the distance along the fiber. The vertical is the strain, so we can map the strain distribution along the sensor. So by looking at the sensor signal, we will know if there's a crack or if there are multiple cracks, and if there's a crack, what is the location and what is the crack width. So based on this understanding, we developed a two-way strain transfer analysis. Basically, we were able to convert the measurements from the sensor to the real strain field condition, meaning that if you deploy a fiber optic cable in a structure like a concrete block, then from the readings of the sensor, you can accurately determine the strain distributions, and similarly, you can determine temperature distributions. Then how can we use this in material research? As I mentioned, my collaborator, she's a materials expert, work mainly focusing on concrete or cement-based materials. According to ASTM's test standard, we assume the concrete material has uniform shrinkage because of the, for example, the water loss during the reaction. There's the volume change. And we assume this volume change is uniform, but according to our measurements, we found that it's actually not uniform. Therefore, it's important to characterize this non-uniform strain, shrinkage strain, so that we can better characterize the materials. And based on the basic application materials, then we apply this sensor technology for structural elements. We tested the pre-stressed concrete beam under 4-point loading, basically bending, and we deploy the sensors at different depths of this beam, as shown by the green lines. So when we increase the load level, we can detect peaks. Each peak represents a crack. So as you can see, when we increase the load from 30 to 61 kilonewton, we saw more and more peaks, and the magnitude of the peak also increased. This means we detected the cracks, and we were able to have a real-time monitoring of the cracks. And we were able to replot this one-dimensional measurements in 2 dimensions according to the location of the sensors. Then we have this plot. The contour shows the initiation and the widening of cracks. Well, this sounds very useful for structural engineers when we want to know more about the failure process. But in real applications, there was a challenge because, as I mentioned, along the sensor lens, every point is a sensor. So one line, just a single fiber can provide you millions of data points per second. So when we apply this to real structures like bridges or buildings, if you have 100 or 1,000 meter sensor, you generate too many data. So human beings cannot analyze data efficiently. Even though we can get real-time data collection, we cannot achieve real-time data analysis. So this motivated us to develop an AI approach to do the data analysis automatically. We developed the different types of AI algorithms to process the data automatically, and then we solve this problem. So because of time, I'm not going to elaborate the details of the machine learning methods, but based on this machine learning method, we developed a digital twin based on the BIM software. So this digital twin can collect and analyze and predict the structural behavior in real time. This will currently we are combining this with the finite element analysis to develop the mechanics-aware digital twin model for structural management. So I will skip some methods for machine learning. Another application is that we can use this type of sensor technology to monitor interface debonding or delamination. So for example, we apply ultra high performance concrete to repair damaged concrete slab. We can cast a layer of ultra high performance concrete, but at the interface, because of the different shrinkage behavior, there will be a debonding. So currently it's very hard to monitor this debonding behavior. And then we use the distributed sensor to monitor this. And based on our monitoring results, my collaborator was able to further improve the design of the material so that we can minimize the interfacial delamination. So here are some results, and we did some dye penetrate testing to validate the measurement results. We also apply this sensor for out-of-plane or buckling measurements for thin-walled structures. Thin-walled elements are very widely used in aircraft. So we use distributed sensors to monitor the full-field buckling behavior instead of single-point measurements. And we also collaborated with Department of Transportation and applied the sensors to concrete pavements. And this was conducted in Minnesota with Minnesota DOT, and we were able to monitor temperature, strain at the same time, and cracks to better design the pavement. Then I want to briefly introduce our work with the National Institute of Standards and Technology for fire research. We developed high temperature fiber optic sensors for structural fire applications. So we did this calibration of the sensor together. Interesting part is that when we talk about high temperature applications, the Young's modulus of fused silica it shows the dependence on temperature. And we have to consider this because this will affect the results, and we did the thermomechanical analysis. Eventually, we were able to very well calibrate the temperature effects on the measurement results. And we found that when the temperature was not higher than 800 Celsius degree, the measurement was okay based on our thermomechanical analysis. We get accurate measurements. But when the temperature was higher than 800, the measurement became unstable. This is because of the material properties, because the fused silica will have some chemical reactions at high temperature. Then we developed a thermal annealing treatment method. Then we increased the measurement temperature from 800 to 1100. So then this is good for fire applications. We grilled some reinforced concrete beams and steel beams in real fire. And we also extended the applications to composites, steel concrete composite slabs. Then why do we do this? Of course, we wanted to know the temperature strain distributions, but more importantly, we want to develop enhanced method to monitor to collect the data so that we get more reliable analysis of the structural behaviors. Because in fire, there's a very complex temperature distribution. As Professor Nino, the fire dynamics is very complex. So it's very difficult to predict the temperature distribution within the structure, like in the building. But if we get accurate measurements of temperature, then if we know the relation between temperature and the mechanical properties, we can very accurately predict the structural behavior, like what will be the failure time, what will be the remaining life. And based on the success of the small-scale testing, we did some large-scale testing in the National Fire Research Lab at NIST. We get good results. Then I want to briefly talk about some chemical sensing or biosensing work. So we developed some fiber optic sensors with functional coatings based on nano fabrication technologies. We want to make sure the fiber optic sensor is responsive or sensitive to the parameters that we want to measure. Because of time, I'm going to elaborate all of these stories, but if you have interest, I would like to talk more with you. So initially, we started with current sensors. We apply some functional coatings. But the problem is that in real structures like reinforced concrete structures, we don't know where the corrosion will happen first, right? What is the most dangerous location? Then you have to deploy a lot of sensors. And then how can you manage the cost and the later operation of the sensors? If one sensor is broken, go to replace that will be very complex and costly. Then we developed a distributed fiber optic corrosion sensor, just one cable, get continuous measurement. The sensor itself also serves as the transmission line. So basically just a fishing wire collect all the information without extra cables. And but structural engineers were concerned, hey, we don't want to wrap some cables on the surface of the steel bars because that will reduce the interface bonding, right? So then we did some pull-out testing. We show that when the spacing of the cable is not smaller than 10 millimeter, which is about half inch, then we are okay. But in real application, we can even increase this spacing to reduce the cost. And then we apply this to monitor fiber reinforced concrete. We put this in salt, let it corrode, and then we monitor the strain distributions. Then based on the strain distributions, we have a mechanical model to quantify the mass loss because of corrosion. So basically, we were able to not only detect whether corrosion happens, but also we can locate and quantify the severity of corrosion. So we also received funding for pipelines. So pipelines and the rebars, they are very similar things, right? So we easily translate this technology to monitor pipelines because pipelines are very long. So this technology becomes perfect for them. And again, in real applications, there's always the challenge for data analysis, right? We get the data, we collect the data in real time, but we just cannot utilize the data in real time. So again, we developed the machine learning methods to solve this problem. So if you sensor collect the data, then this data is provided to machine learning model. Machine learning model process and analyze and interpret the data, provide you the results. And if you have a digital twin model, then you can better utilize the data for structural management. And as Professor Pei and Professor Pang introduced about the CLT buildings, so recently we collaborated with Lehigh University to use our sensor technologies to monitor the CLT building. This panel is a self-centered panel. You don't see, but there's a pre-stressed post-tension pre-stressed tendons in the middle. And our purpose was to utilize this distributed sensor technology to measure the detailed strain distributions within the different wood panels. As you can see, there are many pieces. This panel was composed of many pieces of wood. And we found that different pieces have different strengths because the load was not uniformly applied to all the pieces. And we also monitored this for a long time to understand the creping behavior because this panel was subjected to the compression load over time. We want to see how the creping is developed and how that will affect the structural behavior. So there are a lot of basic research going on for this. So I'm not going to elaborate too much. I want to introduce a little bit more so that we can talk about potential collaborations. So there are two challenges for this technology. So one of the main challenges is the sensor installation because you have a long fiber, right? How can you install this in structures? So recently we started to work on, have a collaborative research to use the fiber optic sensor to monitor the 3D printing process. In this process, we designed the extruder so that we can automatically install the fiber optic cable during the printing process. The printed fiber is like sensory nerves that can provide a real-time monitoring of the printed structure. We did the 3D concrete printing. We are talking about the building scale 3D concrete printing. So concrete is heavy, right? The high density. So if we print the structure very quickly, before concrete is hardened enough, gain enough strength, the bottom layers will be deformed, right? Because there's compression. So we use this sensor technology based on the maturity theory. We can monitor the strengths of concrete in real time, and then we can maximize the printing process, printing efficiency. We know, okay, if we don't exceed this rate, then we will be okay. So we can optimize the manufacturing process, and at the same time, the printed sensor can provide long-term monitoring. So then I want to briefly talk about our AI research for material design or material discovery. So we proposed this prediction optimization framework. So this is the core concept, of AI-based concrete design. We use this method to develop ultra-high performance concrete, ultra-high performance geopolymer concrete, and some other sensor technology. Sorry, there's something. Why do we do this research? Our main motivation is that there are many types of solid waste. So in the lab, we have developed different materials to utilize the solid waste, like fly ash. But the physical and chemical properties of the solid waste, they always change from batch to batch. Even for the same plants, a different day, they have totally different material properties. So some high-performance materials, they are very sensitive to the raw materials properties. But if you want to develop a concrete, usually one type of concretes require multiple years to do the testing. So it's very efficient. That's why, although a lot of people have shown that in the lab, we can utilize waste materials very well, but in reality, the utilization rate is very low. So we want to develop an AI method to be able to design the cost-effective or low-carbon concrete efficiently so that we can utilize large amounts of waste materials. So we developed machine learning model to predict the concrete properties like compressive strength, tensile strength, rheological properties according to the basic variables like the physical and chemical properties of materials. And based on this mapping of input-output relationship, we utilize the optimization method to optimize the material design. So we have published a lot of papers on this topic. So if you're interested, we can talk more. Our main contributions here was to solve some challenges related to data-driven research. First, the type of challenge is the challenge of data. We don't have a lot of data, and we don't have a lot of high-quality data. Another challenge is that there are many types of machine learning models. So how can we select the best model? Right? You can easily find more than 20, 30 machine learning models. And also there are a lot of parameters. How can we deal with the parameters in the material optimization process? And there are some challenges related to the variety of solid waste. So to solve those challenges, we developed generative AI methods. We have different modules to solve different challenges. For example, we have the automatic data collector. We use our large language model like ChatGPT-based methods to collect the data from published papers automatically instead of manually collecting the data. And we also have data generator. Like if you have seed data, two groups of data, then you can generate a new set of data by returning the characteristics. So yeah, I'm not going to elaborate the details, but we found that this is very interesting. And we also developed AI methods to design structures like buildings, bridges. We can use our large language model-based multi-agent systems to design the structures automatically. At the same time, we want to make sure it aligns, complies with the structural design codes. Because if you just let a large language model to do the design, it could give you totally wrong results. And we developed some programs. Hopefully, this will be commercialized very soon. And for the structures design, so we did some so-called toys-inspired reconfigurable modular structures. Several speakers already talked about modular structures, which are very promising. So we designed some Lego-inspired building blocks. And those blocks, as you know, they can be assembled, disassembled, and then we can reuse the blocks to assemble different structures. Like we assembled a very short slab, like a bridge. It's not a real bridge, but we simulate a bridge. And then we disassemble those blocks and reassemble them for beam, column, frame as a part of the building. So yeah, this is within our circular economy research theme. This research has been integrated with some other sensor technologies and 3D printing. So those Lego blocks have fiber optic sensors installed. So those are actually smart blocks. So in the future, we know we have some tags for each block. Then we have blockchain technology to do the management. So another toy-inspired structure is a transformer toy-inspired technology. So as you know, the Lego blocks are connected using dry connections so that they can be disassembled in the future. Then we developed the adaptive connections. So the connections have some actuators. Then we can adjust the stiffness of the connectors in real time so that, for the dynamic behaviors like earthquake behaviors of buildings is closely related to the mass matrix and stiffness matrix. So basically, we are modifying the stiffness matrix in real time based on the sensor results. And then we can give feedback control for the structural behaviors. We have done some preliminary studies for this. Okay, that's all about my research. We have received the funding from different agencies. Thank you for listening.